In this video, I'm going to talk about one of the most basic and one of the most frustrating open questions in mathematics. It's called the Union-Closed Conjecture. I think of this conjecture as kind of like a taunt from God. I imagine, God sitting somewhere and saying they haven't even figured out the Union-Closed Conjecture. How can they hope to figure out world peace? So the conjecture is just a basic question about sets. Okay, so suppose you have a family of subsets of the elements 1, 2, 3 up to n. Okay, family of sets like this. We'll say that the family of sets is closed under union if whenever A and B belong to this family of sets, then A union B also belongs to the family of sets. And now the Union-Closed Conjecture is the conjecture that for every such family that's closed under union, there must be an element that belongs to at least half of the sets in the family. Okay. So it's a really simple statement. It's been verified for small values of n here, but no one knows how to show that it's true for all values of n, despite a lot of effort. Nevertheless, we do know something, and people have come up with some really smart ideas to reason about this conjecture. So I want to show you a couple of results that are related to this conjecture. The first result that I want to talk about is a relatively simple argument, and what it says is that if f is closed under union, then there will always be an element I that belongs to at least 1 over square root 2 times n fraction of all the non-empty sets in the family. Okay, so this is very far from proving the conjecture, but it does say that there will be at least an element that's in many sets. So let's see why this is true. The basic observation here is that actually if you have any non-empty set in the family, so for any x in the family that's non-empty, then the observation is that x must actually intersect half of the sets in the family. Okay, at least half the sets in the family intersect x. This is the first observation. And why is this true? Well, imagine that you have a set in the family that does not intersect x, so it's disjoint from x. And let's call that set A. Then you can associate to A the set A union x, which must also belong to the family because the family is union closed. And A union x does intersect x. Okay? And if you have another set B that's disjoint from x, you can associate that to B union x. And now you see if A and B are not the same, then A union x and B union x will also not be the same. Okay? And therefore, the number of sets that are disjoint from x, if you put them all here, have to be less than or equal to the number of sets that intersect x. Okay? And that proves that at least half the sets in the family must intersect x. Okay. So how can we use this to prove the theorem? Well, there are two cases. The first case is that you can find an x like this that's small. So the first case is that there is an x as above whose size is at most the square root of n over 2. In this case, you can find an element I that belongs to many sets just by picking a random element from the set x. Okay, pick a random element from the set x. Then how many sets in the family will contain this element? Well, at least half of the sets in the family intersect x, And for every set that intersects X, the chance that that set contains this element is at least 1 over the size of X. Okay, so the expected number of sets containing X, containing I, must be at least the size of the family divided by 2 times 1 over the size of X, okay, which is at least the size of the family divided by square root 2n, because the size of X is bounded by square root n over 2. Okay, so that's the first case. And in the second case, maybe the opposite happens, that actually there are no available small sets, which means that every non-empty set in the family, every non-empty set is large. But in this case, let's just pick a random element from the entire universe and count the number of sets that contain this random element on average. What is the expected number of sets that contain a random element? Again, this is going to be large because every non-empty set in the family will be included with probability the size of that set divided by n. So it's going to be the number of non-empty sets times the size of the set divided by n, which is at least as large as square root n over 2 divided by n. Okay. And this number again is just 1 over square root of 2 times n. So in both cases, we find many sets that contain some element. The second result that I want to show you involves a lot more effort and many clever ideas. And it's this one. It proves that if F is a family that's closed under union, then if you take the sum of all the sizes of the sets in the family, then it must be at least it must be greater than or equal to the log base 2 of the number of sets in the family divided by 2 times the number of sets in the family. Okay. And another way to think about this is that if you divide both sides by the number of sets in the family, this says the average size of a set in the family is at least the log of the number of sets in the family divided by 2. Okay. And that's tight because if you consider the family as sets which are just all sets, okay, all subsets of the elements 1 through n, then this family of sets is certainly closed under union, and the number of sets is 2 to the n, so here you get n over 2, and that exactly matches this bound. Okay. Now, a consequence of this bound is that if you now pick a uniformly random element from the entire universe, then the expected number of sets in the family that will contain that element will be at least a log of f divided by 2n fraction of all the sets in the family. Okay. So in particular, if the number of sets in the family is very large, it's exponentially large, let's say 2 to the n over 10, then this would say that a constant fraction of the sets in the family must contain some element. Okay. So it gives a result, a strong result for very large family of sets that's union-closed, that's closed under union. Okay, so this is a really nice result and involves some beautiful ideas. The key idea to understanding this result is an idea that's very powerful and used all over combinatorics, And the idea is usually called compression. Most notably, compression is used to reason about things like the isoperimetric inequality in the hypercube. Okay. The idea of compression is that you can take any family of sets and modify it in a very simple way. And what do? You try to add, in each step, you try to add an element to all of the sets. Okay. So you try to add, say, the ith element to each set. And how do you do that? Well, if the set A union I already belongs to the family, then you do nothing. You leave the set as is. But if the set A union I does not belong to the family, then you add the ith element to the set. Okay, so this is what it means to do compression. And what we're going to do is try to add the first element to all the sets of the family in this way. Then try to add the second element, try to add the third element until we've tried to add all n elements, and reason about the evolution of the family during this process. And this is how we will eventually obtain this bound. Okay. So let me show you some pictures to explain what is happening and what this process looks like. So here's a way to visualize a family of sets. In this picture, every node here corresponds to a set. This corresponds to a set that includes all the elements in the universe. And this corresponds to the anti-set. So every node corresponds to a set. And the sets here, these sets correspond, these are all the sets of size 1 over this universe. Okay, this is the set that contains just the last element. This is the set that contains just the second last element, and so on. And I've drawn, this is a hypercube, so there's an edge between two nodes if the two sets disagree in exactly one element. Okay. And what's shown here, the black nodes here, they correspond to a union-closed, a family of sets that's closed under union. Okay, for example, if you take the union of this set and this set, you obtain this set. If you take the union of this set and this set, you obtain this set. You can check that this family of sets is closed under union. So given such a family of sets, what we're going to do is try to compress it. So we'll try to add elements. So in the first step, we'll try to add the element 1. And that means for every set here, we're going to try and move it up to a set that corresponds to A union 1. Okay. So we're trying to move all the sets here up these red edges. And here's what happens when we do that. So some of the sets move up. The other ones are blocked by sets that are already in the family and don't move. Then in the next step, we'll try to use the 2 edges to add 2. And here's what happens when we do that. Then we'll use the 3 edges and try to add 3 to all the sets. And this is what happens. And in each step, so after we've tried to add 3, we obtain the family F3. That's the family of sets that we have after the 3rd step. And then in the 4th step, we try to add the 4th element. In the 5th step, we try to add the 5th element. Okay, and so we end up with some family of sets in this way. Now, you can track the trajectory of an individual set during this process as well. Okay, so here's a set A that's in the original family. And then we try to add 1, and A moves to this location. We call this set A1. Then we try to add 2 to all the sets, and A moves to this location. We call that A2, and so on. So here's A3, this is A4, and this is A5. Okay, so every set in this process has a trajectory that we can keep track of. Now, here is the key technical claim of the proof. It says that if your family is closed under union, and if you have two sets A and A union B that are distinct from each other, then after you try to add an element, let's say you try to add the element 1, the sets A1 and A1 union B will also be distinct from each other. That's the first claim. And moreover, the sets A1 union B will belong to the new family, and the set A1 union B union 1 will also belong to the new family. Okay. This is the key technical claim. And this claim is actually extremely powerful. It has all kinds of consequences, as we'll see. But let's first try and prove the claim. Okay, so to prove the claim, there are basically two cases. So we're trying to add 1, so let's imagine the 1 edges in the hypercube. Okay, all the red edges that correspond to adding 1. The first case is that both A and A union B belong to the same edge, the same 1 edge. In this case, basically nothing interesting happens, right? When you try to add 1, A1 remains in the same location as A. Okay, and then it has to be the case that A1 is here and A1 union B is up here. So you see that A1 and A union B remain distinct. Moreover, A1 union B is in the family F1, and A1 union B union 1 will also be in the family F1. The more interesting case is if A and A union B belong to distinct edges in the cube, distinct 1 edges. In this case, the first part of the claim is true because we're only moving sets along an edge, so A1 and A1 union B, A1 is going to belong somewhere on this edge, and A1 union B must belong somewhere on this edge after we try to add 1 to A. So A1 and A1 union B will be distinct. Now, after we try to add 1 to the set A, well, what's going to happen, and to the set A union B, which both belong to the family, these locations will have to be occupied in the family F1, right? Because A belongs somewhere on this edge, and we're going to try to add 1 to it. A union B belongs somewhere to this edge, and we're going to try to add 1 to that too. So these locations will be occupied in F1. And if you think about it, the only thing we need to prove now is this claim that A1 union B and A1 union B union 1 both belong to the family. Well, both of these sets have to be located on this edge. So the only problematic case here is that one of these sets does not belong to the family F1, and that can only happen if this set does not belong to F1, and moreover that set is equal to A1 union B. Okay, because A1 union B union 1 has to be located here. But if this set is A1 union B, then A1 has to be down here. A1 cannot contain 1, which means that A has to be down here, and A union B has to be down here on this side. And I'm going to explain why this cannot possibly happen. And that's because if A and A1 are down here and they're the same, it means that A was blocked from moving up when you try to add 1 to A. So there must be a set C here that belongs to the family F. But now you have C that belongs to the family F here. A union B is down here and it belongs to the family F. So that means the set A union B union C must be up here and belong to the family F. And therefore, A union B will also be blocked from moving up when you try to add 1 to it, okay, because it's blocked by A union B union C. So this location must actually be occupied. Okay. So the result is that the claim has to hold in all cases. Now, let me explain a couple of consequences of this claim. The first consequence is that actually F1 must be closed under union. And that's because if you take any two sets, A1 and B1, that belong to F1 and consider their union, well, if A and B are distinct, then either A is not equal to A union B or B is not equal to A union B. So let's assume that A is not equal to A union B. And now we apply the claim. A is not equal to A union B. We apply the claim. And then you see that A1 union B1 has to be equal to either this set or this set. But both of those sets belong to the family. Okay, so A1 union B1 must belong to the family. Right, so this proves that the family F1 must be closed under union. But now you see that actually what we showed, we just starting from the assumption that F is closed under union, we showed that F1 is closed under union. And then applying exactly the same reasoning, that shows that F2 must be closed under union, F3 must be closed under union, and we must get that actually all of the sets during the evolution of the compression operation must be closed under union. Okay. So that's one consequence. And a second consequence is that actually for every element I, if you take an element an of the set, the final family Fn that we get after doing this process n times, an an union I must also belong to the family Fn. Okay. In other words, the family Fn is sort of an upset. For every set that belongs to the family Fn, all supersets of that set must also belong to Fn. So let's prove that. Well, there are kind of two cases. The first case is that I belongs to AI. And if I belongs to AI, then this is clear because AI, when AI becomes an, it only gets bigger. So this would imply that I belongs to an. And that's equal to an union I. And that means that an is equal to, so this means that an is equal to an union I, and an certainly belongs to the family Fn, so an union I will also belong to the family Fn. The second case is that I does not belong to AI, but in this case we consider the sets AI and AI union I. Both of these have to be distinct, okay, because I does not belong to AI, and moreover both of them have to belong to the family Fi. Okay, because AI certainly belongs to Fi, and then we try to add I to the set AI minus 1 in the previous step, and that means that AI union I has to belong to Fi, whether we succeed in adding it to AI minus 1 or not. Okay. So now I have two distinct sets, AI and AI union I. Think of this I here as the B here, and they're both distinct. So applying the claim, we'll get that AI and AI plus 1 and AI, ai plus 1 and ai plus 1 union I will both belong to f I plus 1, and both will be distinct. And then applying the claim again, we'll get the same statement for fi plus 2. And continuing this way, we'll eventually get the same statement for fn. Okay, and that proves that an union I belongs to fn. So that's another nice consequence. And then there's a final consequence, which is about a structure called an interval. So given a set A now, I can define the interval A to AN, and this is a collection of sets X that lie in between A and AN. Okay. Sets X that lie in between A and AN. And I'll denote that collection of sets by this diagram. And another consequence of this claim is that if you have two distinct intervals, so if A and B are distinct, and you have the intervals corresponding to A and the interval corresponding to B, then the claim is that these two intervals must actually be disjoint. Okay. In other words, A has some trajectory that goes through this interval here, and B has another trajectory. But not only can these two trajectories touch each other, they actually have to remain quite far from each other. The entire intervals have to be disjoint. Okay, and that's because, by the claim here, if you have two sets A and B like this, then either A is not equal to A union B or B is not equal to A union B. So let's assume that A is not equal to A union B. Then I can apply the claim, and since A and A union B are distinct, we'll get from the claim, after repeatedly applying the claim, that AN and AN union B must be distinct. But that's not possible, because AN contains this set that's in the common intersection of the two intervals, and this set contains B. So AN must contain B if these two intervals intersect. And if that's the case, then AN would be equal to AN union B, which contradicts the claim. All right, so all of the intervals defined by the trajectories have to be distinct, have to be disjoint. So here's the picture that we've now arrived at. We run the compression process. We end up with a family of sets Fn, and this entire process defines a bunch of disjoint intervals, like these ones. And moreover, the final set Fn is an upset. That's what's captured by this first point. And now we're going to use all of these properties to give a bound on the size of the average set in the family. So let's do it. So I have a picture here to help me count some quantities. But the first observation I want to make is, so we want to calculate now, we want to estimate the size, the sum of the sizes of every set in the family. And that's equal to the sum over A of the size of AN, but this is larger than the size of A in general. So to make this correct, I need to subtract out the size of AN minus A. That's the number of additional elements I added. So that's the first observation. And second observation is that I'm going to try and count the edges in this picture, the edges touching every edge, every set AN, in two different ways, and that'll give me an inequality. So on the one hand, exactly n edges touch every set AN. Okay, so I have the sum over all A of n. This is n times the number of sets in the family. And I claim that that must be at least as large as the sum over A of 2 times the 2 times n minus the size of an. This is because n minus the size of an is the number of black edges that touch an, namely the number of edges that go from an to a superset of an. Okay, the number of edges you obtain by adding exactly one element to an. And there are n minus the size of an options for how you can add a single element to an. Okay, but every such black edge that we've counted here on the right hand side is counted twice on the left hand side, because this black edge, for example, is counted once here, once by this set, and once by this set. So if I take count all of these black edges from below and multiply that by 2, that can only be less than or equal to the number of edges counted on the left hand side. But now we can add, there are even more edges counted here, namely there are these blue edges. Those are the edges that go from an into the interval that lies below an. And how many blue edges are there? Well, there are the number of blue edges is the same as the number of elements in an that are not in A. Okay. So I can add them in, and the left hand side is still larger. I've ignored some edges, like these edges that go below but don't go into the interval. Okay, and that's why I have an inequality here. So that's a calculation. And now let's combine these two bounds. Let's compute 1 plus 2 divided by 2. That gives the sum over A, the size of A. This n here cancels one of the n's here. So I get that it's at least the sum over A n over 2. And this an here is cancelled by this term. And what's left is 1/2 of the size of an minus A. So now the only term we need to estimate is the sum of all such terms, and this is where we'll use the fact that all of these intervals are disjoint. So what can we say about the sum over A of the size of an minus A? Well, it's equal to the sum over all A of log of the size of the interval from A to an. Right? Because if an minus A is k, if there are k elements added to an, then the size of the interval is 2 to the k. So if we take the log base 2 of the size of the interval, we recover the difference in the set sizes. Now I can express this as the number of sets in the family times, I'm going to add 1 over the number of sets of the family, so that this quantity here looks like an expectation. So it's an expectation of a log of a number. And the log function is concave. The log function is concave. So this can be bounded by the number of sets in the family times log of the expectation, the expected size of an interval. Now finally, I want to use the fact that the intervals are disjoint. And that means that the total size of all the intervals here is at most 2 to the n, because all the intervals are disjoint. So I get that this is at most the size of f times log of 2 to the n divided by the size of f, which is equal to the size of f times n minus log of the size of f. Okay, and putting this calculation back, putting this estimate back in here, we obtain, the n's cancel out. This n over 2 cancels out with this n, and what you're left with is exactly what I claimed. Okay, that this quantity must be at least log of the size of the family divided by 2 times the number of sets in the family. Alright, so I hope you enjoyed that proof. It involved a lot of nice ideas. And I think it's really cool.